V, add them up and transform, that is T of V plus W, it will be TV plus TW, right? And similarly, if you take a vector, scale, and then transform, it's as good as transforming and scaling, right? So alpha times V would be alpha times transformation of V. This is true for all VW in V. I think I should have used, let me use U instead of. Okay, so it looks like there is some it says microphone is not turned on. So can you not hear now? Now? Hello?
You're audible, sir.
Audible? Okay. Fine. So this is about linear transformations. So a specific type of linear transformation is basically matrix, right? So you use matrix to transform one vector to the other. So for example, you can transform a vector in Rn to a vector in Rm, right? This is a typical matrix based transformations, and it's obviously linear, right? So this is also linear. Okay, linear. Okay, so now, so why do you need to study matrix-based transformations? Because in many problems, you want to solve some simultaneous equations, right? For example, Ax equal to B, right? If you want to solve such equations, you need to understand what kind of, what is the effect of A on the vectors, and how do you recover X from this equation, right? Towards that, we ask this fundamental question of invertibility of a matrix. Right? So what are the conditions that you need for invertibility? That was the next thing, right? So A inverse. Well, we showed that A inverse does not exist if there exists X not equal to 0 such that Ax equal to 0, right? So if this happens, then A inverse does not exist. But the opposite is not guaranteed, okay? So if Ax is not equal to 0 for every X not equal to 0, doesn't mean that A inverse always exists. So now let's look at the other part of this. Okay, among other things, we also looked at certain transformations, right? So how do you make, supposing, let's say I can transform A, suppose you have Ax equal to B, but A I can write it as U lambda U transpose, right? Some special transformation, then I can solve these equations pretty easily, right? You don't need to compute inverses, but you have to do some matrix multiplication, which is very easy to implement, right? Especially we started out with diagonals, right? So now, of course, this, for example, if I have a lower triangular matrix, let's say A11, 0, 0, 0. This is A12, A21, A22, and then 0, 0, 0, and so on. This is ANN, right? This is called a lower triangular matrix, right? For obvious reason. So now, if I give you a lower triangular matrix, how do you solve this set of linear equations? Ax equal to B. Very easy, right? So if you take the first row here and multiply with x, what do you get? Huh? So the only non-zero term is A11, right? So A11 gets multiplied by the first component of x, let's say x1. So we get A11 x1 equal to the first component of B, which is B1. So from which you can easily calculate x1, right? Done. So what about the second equation? So you get A21 x1 plus A22 x2 equal to B2. How do you solve for x2? Pretty easy, right? B2 minus A22 B1 divided by A11. That is your x1 from the previous equation. So this will give you x2 and so on, right? So pretty easy, right? If you have such a equation. Now, essentially, solving these equations boils down to somehow turning this complicated matrices into some simpler matrices, right? That's why transforming a matrix into simpler matrix is something that we are very much interested in. So let's go back to A inverse and let's look at one small aspect of A inverse. So suppose I have, it's a mapping, right, from Rn to Rn, let's say. Rn to Rn. Because if you consider Rn to Rm, there is no guarantee that you will have an inverse if m is not equal to n. Okay, so now we saw one situation where a single point here should not be mapped by two or more points in the domain of your matrix, right? A, right? So now the other thing that should happen is that is called 1 1, right? So you need 1 1. Onto is what? It should be covered, right? The entire the range space should be equal to Rn. So what do you mean by that? What do you mean by that? You take any point in this, in the range, right? Any vector. There should be a vector here that gets mapped to this vector, right? I'm not saying it should be unique, but there should be at least one vector that gets mapped to this vector, right? So let's write that formally, right? So for any x in Rn, okay, let me write y in Rn. There exists an x in Rn, okay, such that a x equal to y, right? Is that fine? This is should be the case. So what is this y? So this y should be here for every y in Rn in the range of your matrix. There should exist an x here, for example, this that gets mapped to this particular thing, right? So that guarantees that the entire range space is covered, right? Entire Rn is covered as a range of A. So what do you mean by this? Let's look at what is the implication, right? So I can write this A matrix as column vectors, right? So A1 is the first column, A2 is the second column, An is the last column, right? N cross n. I'll multiply it by x1, x2, and so on, xn. That's equal to y, right? So the moment you see such kind of a matrix multiplication, right? Matrix multiplied by a vector. How can I write this? Is there any other way of writing the same thing? We saw that, right? What is that? A matrix multiplied by a vector. So how do I write that? Yes. How do I write that? Huh? Huh? What modification? Sorry. No, sorry, I didn't get. Individual column multiplications. Multiplication with what? See, essentially, what happens is, in this case, this x1 gets multiplied by this first column, right? This x2 gets multiplied with the second column. Do you agree? I mean, x2 cannot get multiplied with first column or the third column and so on. And so on, this xn gets multiplied by the last column, right? So all that you are doing is you are taking the first column of the matrix A, scaling it by x1, second column of A, scale it by x2 and so on, and then add all of them. That will give me the product AX, right? So how do I write this? This is basically summation I equal to 1 to n xi, this is a scalar, multiplied by this ai, right? So this is what we get is equal to, I should get a vector y. So when is this possible? Can somebody tell me when this is possible? This should be true for any y in Rn, right? So I should be able to find x, that means xi's, such that if I use xi to combine the vectors ai, I should be able to get a vector y. When is this possible? Go back to the previous classes, right? So what is the definition? Huh? It's too much to ask for, right? If you say basis and all that. So y should be in the, so basically you take any y in Rn, that should be in the span of the column vectors, right? Do you agree? So in other words, span of A1 through AN should be equal to Rn. This is all it requires. Okay. But as a byproduct, what do we get? As a byproduct of this, you have n vectors of size n, the span of that is Rn, the dimension of that is also n, and we also showed that they have to be linearly independent previously, right? Do you remember that? It has to be linearly independent because ax should not, au should not be equal to av for all u not equal to v, right? So in that case, so there should not exist a vector x not equal to 0 such that ax equal to 0. That means they have to be linearly independent. So putting everything together, what do we get? A inverse exists if the columns of A form a are linearly independent and should span the entire space. What is that called? Basis of Rn. Right? In other words, the column should be linearly independent and it should span the entire vector space. Right? So what is the rank of a matrix? Can somebody tell me? Huh? Right? So that is called the rank of a matrix as of now. Okay, so it turns out that the number of linearly independent columns is also equal to the number of linearly independent rows, which is equal to the rank. Okay, is this clear? Any questions? So I'll pause for a minute and then we'll move on. I want you guys to digest these things. Have you studied these things elsewhere? If yes, then I'll probably accelerate. Yes or no? How many of you think that you already knew what I'm speaking? Okay, one, yes. Anyone else? Huh? No? Okay, so let's move on. So this is about the inverse, right? So we have one result about inverse. Now the question is, how do you find the inverse? And how do you transform matrices in such a way that you get simpler matrices like diagonal or upper triangular and so on, so that I can solve these equations pretty easily, right? Those are the questions that we should answer. Before that, what we will do today is, at least some part of this class, we'll try to look at some algebraic or matrix algebra, meaning manipulations, okay? So not, yeah, so we'll look at some manipulation of matrices, okay? So now let's look at the first manipulation, which is, I take two matrices, okay? So let's say A is R m by n and B is R n by m, okay? Or to make it very general, let's call it as n by k. Then if I look at AB, right? So what will be the dimension of AB? N cross m cross k, right? That will be the dimension. So I can talk about the ijth entry of this matrix. Okay. So what is this? What will be the ijth entry? Can somebody guess or say something about ijth entry? How do you get ijth entry of the product of two matrices? How do you take the product? You take the row multiplied by the columns, right? How do you get the ijth entry? You take the ith row of A multiply by jth column, right? Is that fine? Okay. So now what we will do is, so the answer would be, you take ith row of A times jth column of B. Okay, this is as simple as this. So what is the ith row of A? So when you multiply two matrices, two vectors, right? So that's what I'm doing. I'm taking a row vector multiplied by a column vector, right? So what do I, if I do that, is that correct? Did I make any dimensionality mistakes? No. Okay, so fine. So what do you mean by multiplying a row vector by a column vector? You're taking the first element here, taking the product, second element, taking the product and summing them, right? So I can write this as, for example, ith row, but I'm going to take lth element, right? L goes from 1 to whatever. And I'm taking B. What should I do here? I should look at lth column, right? So whatever. and jth row. So I have to sum it over all L. L goes from what to what? J is the, so L is the number of columns, right? So this is N. This is fine. So the ijth entry is AIL, BLJ, summation over all L will give me this. This is very easy. Okay. Now, this is the first one. So suppose I look at what is trace of a matrix A? Sum of the diagonals. Okay, of course, this should be n cross n. Okay, otherwise trace is undefined. Okay, so this is summation I equal to 1 to n A I. Right, I'll look at the diagonal entries and add them. I get trace of A. So now let's look at what is trace of AB. Now, if I have to write this, then AB should be square matrix, right? Otherwise, trace is undefined. So this could be, for example, M cross N. This could be N cross M. Okay. Then the resulting matrix will be M cross M. So you have the trace. Okay. So what will be the trace of AB? All that I have to do is I have to take the diagonal entries of AB. So what are the diagonal entries of AB? So I know the ijth entry of AB, right? So this gives me the ijth entry. So I have to look at ith entry. So that's pretty easy. So L equal to 1 to n AI L B L I, not J, right? This will give me ith, and you have some overall I, right? So I equal to 1 to M, right? This will give me the trace. So keep this in mind. Okay, so get used to these things. Almost trivial, but you should get used to it. Okay. Okay, so any other things that you have seen? So one more last thing. So suppose I have two matrices A and B square. What is trace of A plus B? Yeah, it's trace of A plus trace of B. This is also easy. And then finally, trace of, suppose I have a scalar and what do I get? Alpha times trace of A. Is that correct? This is pretty trivial, right? Okay, fine. Okay. Okay, now let me ask, maybe I'll write this. So what can you say about, for example, I have two matrices A and B. I'll take trace of AB, trace of BA. Of course, A is M cross N, B is N cross M. Here, B is N cross M, A is M cross N. So BA is N cross N, AB is M cross N. So what can you say about the traces of these two? Yes? Huh? Huh? Is it different or same? Any idea? Those who are online?
So different.
Huh?
Both
Different?
are different.
So why do you say that?
So because the summation of I for the first one will run from 1 to m, and for the second one it will be from 1 to n. I mean,
Okay, so let's try that. So whatever you are saying, right? So what should I do? A I L B L J, right? Is it J or I?
I
I. Okay. So I have to sum it over all L. L should go from the number of columns of A, right? So the number of columns of A will be N. And then I have to sum it over all I. I equal to what? The number
1
of
to n.
rows, right? So the number of rows will be M. Okay. So what happens to this case here? Same thing. B. What is this? I should start from B I L A L J. Sorry, this is I again, right? Right. So L goes from 1 to m, right? Remember, and this goes from I goes from 1 to n. Okay, now are these two equal? Huh? What can you say about this? Equal or no, not equal? Hmm? Question. Is it equal or not equal? Hmm? So what do we have here? So 1 goes from L equal to 1 to n. So that's AIL, right? In other words, I goes from 1 to n, right? So see, let's look at what is happening here. So let's use, so L is this part, right? This goes from 1 to n. Okay. Let's see whether this part goes from 1 to n. No, right? Is that correct? Yeah. So no, let me not do that. So now, how do you prove that both are equal or not equal? What do you think? Is trace of AB equal to trace of BA, or it's not equal? What? Hmm? So why? Right? So how do you show that they are the same thing? Okay, so let's, you are saying replacing I by? Uh-huh. Okay, so let's, this is equal to, you are saying I equal to 1 to M, L is equal to 1 to N. Okay, so I you are making L and L you are making I. Okay, right? Is that fine? Okay. Anyway, so let's not waste too much time on this. Check. Okay. Fine, but keep this in mind. Okay. So fine. Now, okay. So, okay, I think I pretty much covered most of the basic algebraic whatever. Okay, so one more thing. Suppose I take this vector, okay, so A1, sorry, not this. Okay, and I multiply it by another vector like this. So what do you get? Let's say this is n rows, one column, and this is one row, n column. Okay, so what is the what do you get? You get a matrix, right? What is the dimension of a matrix of this matrix? N cross n, right? So now, what can you say about this matrix? This is a very easy decomposition, right? So it says a column vector times a row vector. It's called outer product, right? So what can you say about this matrix? Maybe think about rank of this matrix, okay, to be very specific. What can you say about the rank of this matrix? Is it full rank? So let's ask this first question. Is it full rank? Yes. How many of you think that it's full rank? Raise your hand. Okay, how many of you think that it's not full rank? Something called rank deficient, right? So whenever it's not full rank, we will call it as rank deficient. So how many of you think that it's rank deficient? Only two? What about the rest? Don't care? Yes, so yes, Sumant. Hello, Sumant, you wanted to ask a question? Okay. How many of you think that it's not rank deficient? No? Okay, why do you think that it's rank deficient? Hmm. Hmm. Okay, so that's one way, but there is a simpler way, right? So if I can show that, for example, ax equal to 0 for some x not equal to 0, you are done, right? It should be rank deficient. That's what we saw. So how do you show this? Well, all that we have to do is I have to find an x such that b times x is 0, right? b1 times x is 0. So all that we have to do is, let's say, b1, b2, bn times, I have to find something here that will give me 0. Can somebody tell me what is it that I have to fill in here? Okay, assume that this bn is not equal to 0. Okay, I can always assume that. So what I will do is I'll put 1 1 1 1 till here. The last one, right, I will do the following. So if I put 1 1 1, I'll get b1 plus b2 plus b3 till bn minus 1, right? So I have to subtract that. So what do I get here? I'll get bn times the last entry. Let me call that as some x bar. Okay, this last entry. That should be minus b1 plus b2 plus etc. bn minus 1, right? This is what I should get. So in other words, x bar should be minus b1 plus b2 plus etc. bn minus 1 divided by bn. So that's why I need bn not equal to 0, otherwise you cannot divide. So all that I will do is last entry, I will choose it this way. So when you take the product, you get 0. And this vector is definitely not 0 because you have 1 here, right? Do you agree? So it cannot be full rank, definitely. So what do you think is the rank of this matrix? We'll probably revisit, or you can think about it later, okay, after a few classes. But what is the rank of this matrix? Rank 1. Why? I can always find n minus 1 orthogonal, whatever, so-called orthogonal vectors, right? So I haven't discussed about orthogonal vectors, but you can find so many n minus 1 such vectors, right? Okay, so it's actually rank 1. You'll be able to mathematically verify it once I discuss about inner products and so on. Okay, okay, so let's move on to how do you invert a matrix. Okay, then we will look at other transformations. So let's look at what is called matrix transformations. Okay, so what is matrix transformations? Let me give you some ideas. Okay, so ax equal to b. I want to solve this, right? Suppose I take this a, okay, and I do some transformation to get a1, and I do some transformation to get a2, and so on, and finally I get a matrix called identity. So I hope everyone knows what identity matrix is, right? Diagonals being 1 and 0 of diagonals. So now if I have this, right, so how do you get a1 from a? Let's say I multiply a, pre-multiply a by e1 to get a1. If I pre-multiply by e2 to get a2, and so on, and finally I get I. Okay, so if that is the case, right, so essentially mathematically what does it turn out to be? So I take a, multiply by e1, multiply by e2, and so on, multiply by, let's say, m times em. So I'll get identity, right? Well, this transformation is what is called a linear transformation. Then only it amounts to multiplying, right? Otherwise it won't be multiplication. Okay, so if I get this, what do you think is the inverse? Well, remember, inverse exists provided I can go from I to this to this, and so on, from here to here and here to here. if I can do that, that means the each transformations are individually they are invertible, then A inverse is what? This whole inverse, right? So this is basically em dot 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 e2 times e1 whole inverse, right? This will be your A inverse. Okay, so in other words, if I take a matrix, keep on doing some transformations that are invertible, okay, until you get identity, then I can go back also, right? But the point is, these transformations should not be complicated transformations, right? So if it's like complicated, then you can as well directly see how to invert, right? So how to find inverse of A? Yes, question? Huh? Huh. Yeah. Okay. A is this inverse. So what will be A inverse? Okay, sorry. Yeah, you are right. A inverse is that's it, right? This product itself will be your inverse, right? Pretty easy, right? But these transformations should be what is called elementary transformation, right? Something called simple, whatever, right? Then only it makes sense. Otherwise, nobody wants to do this, right? So what are elementary transformations? Let's look at elementary transformations. So what are elementary transformations? Can somebody tell me what do you think is an elementary transformation? Huh? Exchanging of two rows, right? That's any two rows, right? Exchange of two rows, right? That's an elementary transformation. If I exchange row 1 and row 3, right, I can do the reverse, right? What is the reverse? You exchange it this way. So that's invertible transformation. Do you agree? But we don't know whether it's linear or whether it amounts to multiplying it by another matrix. That's something that we should verify. But you understood what it means, right? Do you agree? Okay. So what is the next one? Scaling a row by a non-zero constant. That's true, right? I take the fifth row and multiply by 6. I can get back the original matrix by dividing the 6, whatever the row by 6, right? So that's invertible. Okay. So what is the third one? Replacing a row by a linear combination of other rows. Okay. So replacing a row by a linear combination so what do I mean by that? So you can just for example, I can take a row, multiply it by a constant and add it to the previous row, and the resulting vector is what I'm going to write, okay, of rows, right? These are elementary, right? But the only thing is you should be able to check that, you should be able to get back, right? First two things are very clear, right? Very easy. What about the next one? Okay, just to convince ourselves that this is invertible transformation, we don't know whether it's linear. So suppose I have this vector, okay, so A, and you have another B, okay, and you have in between also, okay. This is a matrix. So I'm going to replace B by lambda A plus beta B, okay. So that's what I'm going to do. A as is dot 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 lambda A plus beta B dot dot dot. Okay, I know what lambda is, I know what beta is. Okay, so now can I get back the original? Easy, right? I know that I have taken this particular row, so I know A, right? I know lambda A, I know beta, but I don't know B, right? I have to get back B. So, but I know lambda A plus beta B, I know everything except B in that, right? So I can get back. Is this clear? It's invertible. Okay, so that means this is also invertible. So all these elementary operations are invertible. Okay, Fine. So now, if they are invertible, let's look at what does it translate to in terms of matrices, right? So let's look at the first one, exchange of two rows. So let me have a matrix like this, A1, A2, and so on, AN. Okay. I want to exchange, for example, A1 and A2. So what is it that you will multiply so that you will exchange these two matrices, these two vectors? The first row should be exchanged by the second row, basically swap. What should I do? Whenever I multiply it, the first row should be the second row, right? The second row should be the first row, right? The remaining should remain as is. So what do I do? See, this is what I can do, right? 0, 0. What do I get now? If I multiply this, so it will select the second row, right? Naturally, right? So the first row will get second row, but second row I should get first row. What should I do? Right? Okay. Exchange is done, but what about the rest? Rest should be identity matrix, right? So whatever. So how do I select? Third row should be chosen by this. So this means 0, 0, 1, 0, etc. 0, 0, 0, 0, 1, 0, etc. 0, and so on, 0, 0, etc. 0, 1, right? That's how it should be. So what is the relationship between this matrix and an identity matrix? Huh? What is the difference between this and identity matrix? If I swap the first, so if I take this matrix, right? If I swap the first and second row, I get identity matrix. Do you agree? So it's in some sense, but not in some sense. It's basically permutation of identity matrix. If you take an identity matrix and permute and multiply it with another matrix, it's essentially equivalent to swapping the rows, right? Is that clear? Okay, so multiplying by permuted identity matrix. I'll call this as n cross n identity, whatever. Okay. Okay. So what about the second one? Multiplying a row by a constant. So how do you do that? Same thing, right? So for example, if I want to multiply the ith row by lambda, all that I have to do is take the identity matrix, put lambda in the ith entry, right? Ith diagonal, right? That's all I have to do. Is this easy? So this is the second one is easy. Okay. So what about the last one? I have to multiply one row by some constant, the other row by some other constant, add them to get this. So what should I do? Yes. What should I do? Huh? See, you know how to multiply constants, right? So let's do step by step. So what should I do first? Let's say I want to multiply by, let's say alpha here and then say beta here, one in between, and then identity 0, 0. So what does this give us? It will basically multiply the ith row by alpha and jth row by beta, right? So accordingly. Now I have to do what? I have to add them to get the next one. So how do you do that? So let me call this matrix as B. Okay, B will give me appropriately multiplied. Okay, so I should not do this, right? What should I do? If I do this, then okay, so I'll take this back. So if I do this, that's not enough. So let's look at a simple example. Okay, so maybe a 3 cross 3 matrix. Let's say A1, A2, A3. So I want to get, for example, A3 as alpha times A1 plus beta times, okay, so this is A1, A2, this is alpha times A1 plus beta times, well, what should I take? I cannot take A2, okay, not the linear, I should also include this. right? Some constant times this plus some constant. So I cannot exclude A3. If I exclude A3, what will happen? See, one row is a linear combination of the other two rows, and you are changing the property of the matrix, right? Completely. That's not allowed. Okay, I think maybe I should. Okay, so I should caution here. The row under consideration should be included. Okay. 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 So let's see. So how do you write this thing? Beta alpha A1 plus beta A3. What should I do? Right. So you have basically 1 0 etc 0 0 1 etc 0 identity, right, and so on. Okay, so 0 0 etc there'll be the okay 0 etc, maybe I'll write it like this, 1 0, right? The last row, if I write all 0 except last, which is 1, I'll get identity, I'll get back the original matrix. So what should I do? I should take alpha in the ith entry here, beta in the jth, no, not jth, the last one, right? I should include the last one. So 0 elsewhere. Okay. If I do this and multiply by, for example, A1, A2, A3, what do you get? The last one would be what? It will select the ith row. Okay, so I here is ith and jth could be at least 1, 2, 3, right? So, but in general, this is what? Let's look at an also. Okay, you have n cross n. So in this case, it will select the ith row, multiply by alpha. It will select the jth row, multiply by beta, and it will sorry, the last row and multiply by beta and add them, right? So this is another elementary. This is also an elementary matrix. Okay, it's an elementary transformation. So what is this? So essentially, you are not only permuting, you are adding some alpha, beta here and there, right? So it's an invertible transformation. Okay. So now, what is the use of this? So maybe we'll look at one simple example. What is the time now? Yeah. Okay. So and then I won't continue with this because after this it's pretty easy. You can just look at textbooks that will show how to move forward. Okay. So let's look at one example. Maybe 1 2 2 1. Do you think this is independent? Full rank? What is the rank of this matrix? 2, right? Because all the columns are linearly independent. Now I have to convert this into an identity matrix by using row transformation. So what do you think you should do? See, I already have 1 1 here, right? So I have to somehow ensure that I get 0 0. So what do you do? Huh? What should I do? What is the first thing that you do? Multiply. So let's consider this. Okay, I want to knock this guy off, right? So I want to make this 0. So what do I do? Multiply the first row by 2 and subtract the second row, right? Okay. So what do I do? R2, the row 2 is what? 2 times R1 minus R2. Okay. So what do I get? 1, 2, 0. I have to multiply the first row by 2. I'll get 4, right? Subtract the second row. 4 minus 1 is 3. Okay. So what should I do after this? I have to knock off this guy, right? So what should I do? So R1 is what? R1 minus 2 by 3 times R2. So what do I get here? I don't, there is no problem with this, right? I'll get 1 itself. This will be 0, 0, 3. Now what do I do? R2 by 3, right? Because alpha times a row. So this will be R2 is R2 by 3. So this gives me identity, right? All these are elementary operations which are invertible, right? So what is the inverse of this matrix? So you have to find what is this matrix, what is this matrix, what is this matrix. Take the product, that will be your identity matrix, right? Is that fine? So this is very, very important. Okay, so if the matrix is invertible, I can write the inverse of that matrix as product of elementary matrices. Okay, so I'll write this as a result. So if A is invertible, then A inverse is basically product of E1, E2, etc. some EM, where EI is an elementary matrix. Okay, so this is an important property. You should always be able to get that. Okay. Okay. Any questions? So maybe I'll pause for a minute and then we'll move on. Any questions? No. No questions? Those who are online? No questions? No? Is this fine? Okay. So then maybe we'll look at a couple of properties of inverse. Okay. So what can you say about AB whole inverse? Okay, first of all, what is inverse? So we say that A inverse is the inverse of A. If A inverse is same as A inverse A, which is equal to identity, right? That's the definition of inverse. So what is AB inverse? How do you prove this? This is an inverse? Easy, right? So I have to multiply AB by this, then you'll get identity naturally, right? Trivial. What will be A transpose inverse? Huh? A inverse transpose, right? Why is that? Why is that? Okay. So before that, I want to ask one more thing. You know what a transpose is, right? Make rows to columns constitute rows. What is AB transpose? Huh? B transpose? A transpose. So homework. You should do this as a homework. Okay. So how do you show that these two are equal? Easy, algebra, but I want you to write it down and see that this is true. Okay. Okay. Now, if this is the case, so now if let's look at what is the answer for A transpose inverse is A inverse transpose. Why is that? Okay. So what is A inverse? So if A is invertible, A inverse is what? Product of elementary, right? Let's see if we can prove this way. I don't know. Let's try this out. Okay. What is the transpose of this? So this will be EM transpose, EM minus 1 transpose, and so on, E2 transpose, E1 transpose. So what is A inverse transpose? It's A transpose whole inverse. So now how do you show that it's A transpose whole inverse? Can you check that? How do you check that? Yes. Okay. Anyway, I'll leave it as an exercise. Think about this. Okay. So think. Okay. So I think we have learned quite a few things about inverses. Okay. You know how to find an inverse, right? One way is, basically do some linear transformation and take those product, right? That's one way, right? So there are other ways which we will see a little later. Okay, I may not teach you the details of how to find the inverse, but I'll give you a formula. Which, by the way, do you guys know how do you find an inverse of a matrix? What is the way? Complicated way, right? Adjoint and all that, right? Yeah. Okay, so let's not get into the details of why that is an inverse formula for inverse, but yeah, so we will see what is the formula. Okay, so now with this, I think kind of covered many aspects of basic matrix. Let's move on with a few other things. Okay. So let's look at the most important part in data analysis is two things, right? So I can think of data points as vectors. That's the first thing, because I took features and so on, right? The second most important thing is I want to look at the similarity of two vectors, right? So how do you find the similarity of two vectors? What is the notion? Suppose I have a vector like this. How do you find whether they are similar or not? Huh? Okay, what is cosine similarity? Is it just dot product? Huh. So essentially, I should quantify the angle, right? So if they are aligned, I should get very high value. If they are orthogonal, so-called orthogonal, I should get 0, right? That's what similarity is, right? So I should n dimension. 2 dimension, it's easy, right? I can define cos theta, right? It's very easy. But for n dimension, what is cos theta? I mean, there is what do you mean by theta, right? You have an angle theta there. I can know, right? So it's like weird. Even in 3 dimension, what do you mean by angle? Weird. So now, yeah, see, think about it. There are so many angles that I can define, right? So yeah, so there is no one angle, right? And therefore, there is no one similarity. You should look at 3 different similarities. So one natural way of so there should be a way by which we can define similarity of two matrices, two vectors, right? So towards that, we need a definition for similarity that's called, or I'll say similarity. So this is through what is known as inner products, right? And we also need closeness, right? Well, there is a difference between close and similarities, okay? So how do you define close? Two vectors are close. It depends on the distance, right? You have to measure the distance between two vectors, or in general, it's called norms. Okay, so we will see what these things are in the next class onwards. Okay, so we'll try to figure out more properties. Just to, for those who are curious, how many of you know what an inner product is? Okay, fine, good. How many of you know what norms are? I think you would have studied norms in your calculus and other courses, right? Even in linear algebra. Now, I'll give you how many of you know what is an expected value? Probability. Naveen would have taught you, right? What is the expected value of some x? You know what is an expected value of x? Mean value, right? So now I'll define a new inner product, okay? Inner product is like dot product, okay? Okay. Why is this an inner product? Well, it satisfies all the properties of a dot product, right? Dot product is what? A transpose B. It's linear in A, linear in B. It doesn't matter whether you commute, right? A transpose B same as B transpose A, right? And we have all the other properties, right? A transpose A is always positive, non-negative. It's equal to 0 only if and only if A is 0. Similarly here, x comma x is always non-negative provided x is 0, right? So there are similar properties. So now the moment you have the notion of angle, I know how to, or notion of inner product, I know how I can bring in the notion of distance. So what is distance between two vectors? Okay, what is the length of a vector? Easy, right? This is how we define, right? X inner product as root of that. So what will be the length or norm of this thing? Root of x squared, right? How do you define the angle between two vectors? So you take transpose y divided by norm of x, norm of y, right? This is how, because you scale x to make it a unit vector, scale y to make a unit vector, look at the inner product, right? So what is the analog of this for random variables? Surprisingly, you get, sorry, expected value of xy divided by, this is the similarity, right? What is this called? I'll end here. What is this called in probability? Studied something like this. It's called correlation coefficient, right? So that measures the similarity, right? So it comes from somewhere. Anyway, so I won't go into the details of this, but this is just for the sake of curiosity. Okay, so I'll end here. Thank you.